Hi, we present the paper Towards Closed-Loop Additive Manufacturing, a Paradigm Shift in Fabrication, Inspection, and Repair. The motivation of our paper is due to additive manufacturing, or AM's, immense promise as a new manufacturing technique. However, the AM processes, particularly deposition-based methods, have an inherent lack of reliability due to their pre-programmed open-loop workflow. In this work, we propose a novel, layer-wise, closed-loop AM workflow capable of identifying defects and correcting them. In a conventional AM workflow, machine code, or G code, will be parsed and the printer will fabricate the part directly. However, in our proposed workflow, the printed part will be inspected every time a layer is completed and any detected defects will be repaired. This will increase the efficiency of our manufacturing processes and decrease their failure rate. For our work, we use a UR5E arm to mimic the motion platform for an additive manufacturing machine. A large 2.85mm filament extruder is attached to the robot end effector, which was chosen to exaggerate the effect of any defects that occur. Additionally, we mount a custom sensor next to the end effector to scan the printed parts for closed-loop feedback. Our sensor, drawn in the box on the right, uses a laser module offset at an angle from the camera to act as a depth sensor via triangulation. After each layer completes, we perform a linear coverage with our sensor to get a 3D scan of our printed part, which is then passed to the defect detection pipeline. The defect detection compares a reference point cloud, shown in white above, with the scanned point cloud in green below. After aligning the points via ICP, we compare the point clouds directly by their point cloud difference and classify deviations as positive or negative defects by whether they are comprised of excess material or a lack of material. We have separate processes for handling positive and negative defects. Positive defects, characterized by excess material, are remedied by replanning the extrusion trajectories of future layers to avoid adding more material to the defect. On the other hand, negative defects have a lack of material which we need to fill in. After performing the scan and identifying the defect, we inject a repair path in between the transition to the next layer and scan one more time for defects before continuing to the next layer. Here, the replan strategy is demonstrated with the orange block representing a positive defect. After the part is scanned, on the next layer, the arm stops extrusion and lifts the end effector over the defect. If its height intersects with future layers, those layers repeat the same lifting motion. Our experiments show that the repair strategy brings the part geometry much closer to the unaltered, correct dimensions. Next, we show the repair strategy. Mid-printing motion, we unclamp the filament extruder to introduce a negative defect to our part shown in the red outline. Then the printer returns to fill in the void. Our experiments show that our repair significantly compensates for the missing material, reducing the defect percentage 11-fold. Further, we also conducted experiments measuring the ultimate tensile strength of defective versus repaired versus unaltered force testing coupons, where we see that the repaired coupon's maximum load is much higher than the defective parts. In conclusion, our proposed closed-loop method demonstrates an improvement in geometric tolerance, a decrease in defect percentage, and an increase in printed part strength. We believe this work is an initial step towards the development of a new generation of intelligent manufacturing systems that fabricate, inspect, and even repair in a human-like fashion.